let me just give you a welcome on behalf of Center for C-SPAN Scholarship and Engagement at Purdue University in the Lamb School, where we have these workshops where we're trying to introduce people to sort of the tools to analyze video, audio, and text, and that we have so much of. And so today we're delighted to have Chris Lucas, who's a leader in the audio processing and has some important papers that that he's worked on and published and are more in the pipeline. So I'm going to turn it over to Andrea, who'll give him a formal introduction, and then we'll start with his presentation.
Fantastic. Thank you. Just in case you didn't know who that was Dr. Robert Browning. He is the managing director for this, he's the faculty director for the Center for C-SPAN Scholarship and Engagement and the director of the C-SPAN Archives. I'm Andrea Langrish. I'm the managing director for the Center for C-SPAN Scholarship and Engagement, and I'd like to welcome all of you to the video research workshop, Introduction to Advanced Methods and Analysis in Audio Process. We are excited to have leading us in this workshop today, award-winning researcher, Dr. Christopher Lucas. Dr. Lucas is an assistant professor in the Department of Political Science and a faculty affiliate with the Division of Computational and Data Sciences at Washington University in St. Louis. He studies methodology, political communication, and the media. His research is published in the American Political Science Review and the American Journal of Political Science, among other venues. And he has received the Gosnell Prize for Excellence in Political Methodology twice. Ongoing work supported by the NSF, National Science Foundation, develops and applies computational models for the statistical analysis of speech audio. Welcome, Dr. Lucas.
Great, thank you so much for that introduction. Let me now share my screen. Wonderful. It's great to be here. You can all see that, I hope. As was just mentioned, I'm delighted to present to you a paper that's a part of a broader research agenda. This paper is with Dean Knox, a co-author and friend of mine at Penn. I've posted into the chat a link to this paper, as well as a second paper, which we just submitted over the weekend, I think, in case you are curious. And much of this project and sort of ongoing work in this project is sort of supported by an NSF that we recently received. So our hope is through that NSF to make, there are several components to that NSF, but part of it is to kind of make the tools that we develop in this project more accessible and simpler to use for a variety of different audiences, which entails both, improved software, but also improved resources for teaching and a variety of different things. So with that said, I will jump in. So I want to begin with the observation that political science and probably social science more generally already effectively studies speech audio. So what do I mean by that? Well, we study a range of contexts in which fundamentally the actual sort of raw data that we're studying, the context in which politics is occurring, is one in which humans are speaking to each other, which is fundamentally, again, a form of data which is ultimately audio, right? So we study things like campaign speech. So again, there are a host of papers, among them the paper that I posted into chat, which look at the politics of kind of how politicians campaign to and speak to audiences, to mobilize, to appeal to voters, to try to convince voters of particular qualities of the candidate themselves. We study campaign ads. So if you're a political scientist, you're probably aware of a host of work building on the Wesleyan Media Project about, say, things like negativity in campaigning, how campaign ads can mobilize or demobilize, who they mobilize, and the strategic incentives within that context. We study debates, right? So plenty of papers look at what candidates say to each other during public debates, which again are effectively a component of the campaign trail. A large literature studies legislative speech. So the politics again of coalition formation in parliamentary systems, the way that certain members within a coalition might break in certain contexts and so on. And studies, in fact, again, the publicly spoken words within the legislative body, political media more generally, like and in legislative speech, right, we can think about things like archives of congressional speech. In political media in the form of news, right? So things like say news on whatever channel you might have been watching confirmation hearings, right? And the coverage of those things. Now, all of these are domains in which communication occurs, again, through spoken speech. Each of the citations that I put on here, which are a fraction of the total citations in each of these fields, of course, study strictly the text of speech. So in actually trying to learn about these contexts, they discard completely the sort of non-textual components of speech. Now, I'm going to, in this talk, illustrate what we are doing with one particular example to an analysis of the Supreme Court. We're going to look specifically at oral arguments. And again, here are a host of other papers already studying oral arguments. The Dietrich Ino Sen paper, which I threw up here, is the only other application, I believe, which uses the audio of speech. And I believe Bryce has been or will be out in this same speaker series and also does a lot of great work in this area. And so if you were to look at, again, the landscape of politics, it's relatively obvious that a lot of communication occurs through more than just words. But for a variety of reasons, mostly, I think, practical, we often ignore every other component of speech aside from strictly the words. So what are we losing when we do that? I'm going to play for you a brief clip of former President Barack Obama on the campaign trail. And I'm going to ask, as you listen to it, to imagine, again, the kind of emotions and sentiments, the perceptions that you take away from this brief clip. And then imagine that you instead were to try to deliver the same clip, right? So imagine that you spoke these same words. So imagine the experiment where you hold the text of speech fixed. You say the same thing former President Obama said, but you say it versus, again, former President Obama. So let's listen to that briefly. And again, try to keep in mind the differences in kind of how you perceive former candidate and President Barack Obama from, say, how you would perceive a colleague or yourself or your partner saying sort of exactly the same piece of speech.
One voice can change a room. And if it can change a room, it can change a city. And if it can change a city, it can change a state. And if it can change a state, it can change a nation. And if it can change a nation, it can change the world.
So it's my contention that a lot is lost when we use just the text of speech. Again, if you were to ask the undergrads in my Introduction to Statistics course, they would assert that I'm not nearly as compelling or natural a public speaker as Barack Obama, and they would be right. If I were to try to campaign with exactly that same piece of speech, if a speechwriter wrote the same thing for me and I delivered the same text of speech, I wouldn't have nearly the effect on listeners. You wouldn't infer the same things about me as a speaker as you did just then about Barack Obama. So how can we get it back? What are we losing and how can we put it back into the domain of things that we can study quantitatively? So, as I mentioned, much of my work is attempting to build a toolkit for us to do exactly that, to put back into the domain of quantitative study these components of data that are often thought of as too unstructured to be studied quantitatively. So why is that important? Well, again, it's my contention that we lose a lot if we study strictly the transcription of speech. I illustrated that with the brief clip of Barack Obama, and I'll, in a moment, note some citations to papers that, or a large body of literature which sort of studies specifically what is lost. I'm going to then, after that section, describe to you sort of how we think about audio as data. How do we represent sound in a way that we can, again, study with the same sort of tools that we study all sorts of quantitative phenomena. I'm going to talk about the model that we develop, which again, I hope can illustrate more generally the kinds of things we can do with audio. And then I'm going to note in an application, sort of validating and demonstrating how we can validate these sorts of analyses. And I'm going to apply the model to an old sort of debate in the literature on oral arguments, specifically sort of, do they serve a purpose? So I'm going to try to distinguish between theories of oral arguments or of justices in oral arguments in which they either are strategically signaling things to each other or are sincerely pursuing sort of information and trying to learn about the facts of the case. So with that kind of as a bit of an overview of where we're going, what is lost in transcription if we study strictly the text of speech? So we, as humans, it turns out, infer a tremendous amount about speakers by the way that they talk, by their tone. We infer things about their type. So there's a large literature on, say, in psychology about inferring things like dominance in social psychology. We infer competence from the sound of speech. Charisma is, I think, somewhat obviously deeply rooted in notions of kind of how a speaker sounds. But we also infer things that are a bit more variable. So I think of these as sort of being like, you know, the kind of moment to moment things that we learn about a speaker from the way that they sound. And so here you might think of things like emotions. Now, again, it should be obvious that we convey a tremendous amount of emotion by the way that we sound. I remember, so when I first started in graduate school, one of the earliest projects I worked on was a text as data project. And at the time, it was still, I feel like I'm getting old, because at the time, text as data was still sort of seen with some amount of suspicion from some like parts of the field. And often you'd hear someone say something like, oh, well, you know, what about sarcasm, right? What about negation? What about these sorts of components of speech, which aren't just in the words? Now, again, we can learn a tremendous amount about text, but it's obvious that a lot of these sort of things like emotional valence are clearly going to be also embedded in the way that those words are delivered. And so speech tone can then have effect on listeners. It can, again, lead to humanizing the speaker or dehumanizing them. It can make the speaker sound honest, or it can make the speaker sound deceptive. And these are just a small sort of fraction of the kinds of things we can learn about in audio from or about a speaker. So, okay, cool. Imagine that you grant me that the way that humans talk is important for learning about them, and the way that people sound is important for inferring features about them. So how mechanically would we actually get down to the nitty-gritty of taking this wave file on your computer and turning it into data? What's the actual kind of structure of data itself, right? So if in text we think about things like creating a document term matrix, what's the equivalent with audio? So I'm going to start with a sort of stylized example of how we featureize, how we think about turning audio into numerical data that we can analyze statistically. And then I'm going to, again, try to demonstrate that with the model. So we're going to think about speech audio as being composed of utterances. So on this slide, I've noted on the left side, of course, say one utterance. And you can think of an utterance as being something like a sentence, right? So a piece of speech, which is at some sort of level, a coherent section that we might kind of discretize. Doesn't have to be exactly a full sentence, right? Maybe a complete thought, etc. But we're going to think about the utterance as being, again, a kind of sentence length thought. And then within each utterance, we're going to describe and characterize that utterance with features. And so what are these audio features? Well, you've probably at some point, if you took in some old physics course or just looking at a waveform or on some computer, you've seen an audio wave. And so if you've forgotten, right, recall that the audio that you hear, what you're hearing in my voice right now, just pressure in, say, the pressure that's pushing on your eardrums. And that's varying over time. And so in the top of this plot, I've shown, again, one sound wave. And on the x-axis, we have time. On the y-axis is pressure. And our gray line is denoting basically the kind of baseline pressure in the room, or neutral. And then as I talk, you're hearing through your speaker waves, which are the pushing and the then relaxing of that wave against your eardrum. Now from this, we can summarize this. So the raw data, were you to then try to take this as on your computer, that raw data is just recorded as samples of that pressure at different moments in time. So a sampling rate is some very, very, very high rate at which we repeatedly record basically the value on the y-axis at very, very, very small time steps. So we want to do something to summarize that vector of pressure over time in a way that is sort of simpler and also meaningful. So what are those ways that we summarize it? So one way that we can summarize it just from this raw waveform is something like the number of times that this wave is crossing zero. Now it turns out that actually has an interesting acoustical mapping. It sort of will distinguish, say, sounds of like an S from a big vowel. So that's an interesting quantity that we can calculate. We can also calculate just how loud that particular audio signal is at one point in time. And that might map to all sorts of things that we care about. Maybe a politician's using volume to really emphasize their point. But you'll also note in this waveform, there's again a general trend over time. And so from that, we can calculate what that trend is. So this waveform is actually a clip from, I can't remember which song now because I made this plot at some point, but it's a brief moment in a Willie Nelson song. And so Willie Nelson is, as you can expect, singing. And so there is some underlying pitch, some note that he's singing, and we can calculate that. That might be, again, something like, that has a distinct meaning in signal processing. And so that pitch will be a fundamental frequency, the kind of general thing that your ear's picking up on when you're hearing music in the context of music. But then there are also higher harmonics that you're also going to hear, which are going to be distinguishing tone. So for instance, if I played a note for you on a piano versus if I sang a note, right? Assuming I'm a better singer than I am, right? You could tell which one was a human voice and which one was the piano. And that's again, because of all these overlaying frequencies as well. These sort of additional waves that are kind of combined into that larger one. And so we can decompose, or we can transform that waveform from this pressure over time domain through a Fourier transform into energy over frequency. And so what this is basically, you can think about this as being at a given moment in time, what if we were to reconstitute instantaneously what that waveform was with a bunch of other little waveforms? That's kind of a heuristic way, an intuitive way of thinking about what we're doing when we're doing a Fourier transform. And so you're then getting basically the frequencies at each particular moment that went into that individual waveform at that one instantaneous second. And so here we're seeing, again, the energy over those frequencies. So on the left side, we have bassier sounds, on the right side, higher pitched sounds, and so on. So basically the energy in these different ranges. And we can coarsen this to kind of summarize this in a way that's more empirically tractable. So we'll basically just create bins and then calculate the energy within each of those bins as a way to summarize this with a relatively tractable number of features. And so we can then fill in this kind of heuristic plot that I've made, this audio features label with actual features that we can calculate. So we can calculate things like the bassiness, the power and the more soprano ranges, loudness, so the energy, zero crossing, which is the amount of times that waveform was crossing that x-axis, the pitch, formants, which are kind of these these higher things that the wave is composed of, and then derivatives of these features. So basically, how quickly are these features changing over time? And maybe how quickly are the rates of those changes changing, right? So we can calculate first and second derivatives of these features. And then we can do this for all sorts of utterances. So we imagine, again, in a campaign speech, we calculate these features not just for the first sentence, but for the second and for the third and so on, and for every sentence throughout a speech. And so what we're going to do in this particular analysis then is take a conversation or imagine a single person, and we're going to take all their sentences, the utterances, here denoted with these different blocks, and we're going to imagine that each utterance has a particular label. So you can imagine that being like transitioning between being angry and not. You can imagine it being something like maybe a justice asking a question and sounding very sort of skeptical versus seeming convinced. Things that are labels that you could uncover or apply to particular sentences in some set of audio. And then we're going to, in order to recover those labels, we're going to apply the model that we developed to it. So it was recommended that I pause at minute 20 or so. And so I'll take this opportunity to briefly pause if there were any questions before continuing into the model section of the talk. But if there aren't any questions, I'll proceed. So how are we going to then, so as I mentioned, right, we're imagining that this is the structure of the data. We have basically over time a series of utterances. And I should note within each utterance, as you can tell, I've broken up that utterance into different smaller segments. We're going to calculate those audio features within each of those different smaller segments, which we're going to call frames. So each utterance is then going to be represented as a series of frames. And then within each frame, we're going to calculate something like the pitch, the loudness, and these other features that I've described. So the general structure of the raw data is that a given piece of speech will have audio features, which will be broken up into utterances. And then each utterance will be broken up into frames. Each frame will have some vector of audio features which describe it. And then we might have associated with this a host of metadata. So something like who's speaking, what's the topic, right? So we could map to this text, right? So what are they talking about and so on. So how do we then model this data? What's the kind of general approach that we take?
Not using statistics, it's using imagination.
It's in fact going to be using statistics, but we found this clip from Scalia at some point when we were coding data and just felt that we had to use it as much as we possibly could.
Not using statistics, it's using imagination.
So it's in fact, okay, going to be using statistics. So here's the way that we're going to model the data. So we're going to imagine that for each of these utterances, there's a particular label, say something like one of the emotions that you are interested in. So an utterance will have some label, and then we'll imagine that each utterance, given a label, is generated by transitions between sounds that define that particular label, that particular emotion. So here I've denoted those sounds according to colors. And so emotion one will be, again, composed of transitions between different sounds. And then emotion two will be transitions between other sounds specific to that emotion. And now you may be inferring the way that we model this, which is that each of these emotions is going to have for it a particular hidden Markov model, which is going to govern transitions between sounds, which we learn from the data. And so I'll describe that more formally in a moment. But basically what we're doing is transitioning between states when we move from one frame to another. So in frame one, it's assumed that the data are generated from some latent state. We transition to a different state or stay in that state with some probability governed by the hidden Markov model. and so on for emotion 1. And then above that, we're going to have a second hidden Markov, or a second level of the hidden Markov model, which is going to be determining transitions between the emotions. And so if you've seen hidden Markov models, that might make some sense. If not, I'll try to clarify what we're doing in the next few slides. So here's a little bit of notation. This will be the only notation that I use and the only math that I use. I'll talk. Well, this slide and the next, I believe, actually. So, but I'll try to then illustrate everything pretty quickly. So we're thinking about, again, each conversation being a sequence of utterances. So these are those large blocks that I was showing you previously. So an utterance then is each of these. Then each utterance we're going to say has some mode of speech. Now I talked about that being an emotion, but it could be something else. It could be something like who's talking, right? It can be any label that can be applied to a given utterance that would define the way that that utterance basically sounded. And then that utterance is going to have associated with it certain metadata. We'll denote that with W. And that can include the prior mode of speech itself, right? So something like, was the previous speaker angry? Or was the previous utterance angry? And so on. Each utterance is going to be the sequence of frames, which I described a moment ago, denoted here by T, or indexed by T. In each frame, there will be a sound that's produced. I'll let that be R. And then the sound is going to generate audio features. And so these are the actual quantities that we observe. Here, X, indexed by both the utterance and within the utterance, the frame. So we have frame level audio features. And so the general statistical model that we employ then is as follows. So in this first line, all that we're doing is modeling the transition between different modes of speech. So these are the human defined labels like the emotion of an utterance, or whether or not the speaker sounds skeptical or rather neutral. The transitions between those labels across utterance is going to be governed by a multinomial logit. That's all that this is doing, given the metadata. So the metadata is going to then give those transitions according to this big logit. The mode of speech then is going to be drawn from these plausible sets of modes, again, given the transition probabilities between those modes that we're going to get from this big multinomial logit. And then the sounds that that generate the features are going to be drawn given the mode. And then the audio features themselves are generated given the sound. And so there are two hidden Markov models in here. One is the transitions between mode, and the other is the transitions between sounds. The sound states are an unsupervised hidden Markov model. The modes are a supervised hidden Markov model, and all of this, all the parameters in this model are jointly learned. And so if that made sense, awesome. If it didn't make sense, I'll try to illustrate some of this. So, oh wait, and I should note as well, we estimate all of this with the same EM algorithm that you know and love. So we use the forward-backward algorithm, which is common in hidden Markov models. The E step is basically when did the emotions happen? When did the emotional switches happen? So we change our expectations of those two questions: when are emotions occurring and when did the switches occur, as we update again our sound distributions and our transition probabilities, which you can think of as basically being, again, sort of what's the nature of the emotion, what's it like in terms of the data, what's the distribution that triggered those switches. So we're updating basically those underlying distributions. All of this is implemented in a fast C++ implementation in an R package called communication. So the actual inference is easy and can be black boxed. So I'm going to try to illustrate a little bit of that. And so what I'm showing you right now is the raw data from a particular utterance. So on the left and on the horizontal and the vertical axes, we have different features. So in each panel of this figure, I'm plotting or I'm projecting frames of a particular utterance according to different ways of cutting and representing those frames. So we have, in this case, something like 60 some odd features that we've calculated. We're going to look at some 2D projection of all the frames in the 64-dimensional feature space. So this is hard to look at. I'm going to zoom in so you can see a little bit clearer. So, oh, is there a question or? Oh, I'll note, yeah, before I do that, I had two questions. So the labeling could be subjective. That's exactly right. So Yiqiang noted that labels could be wrong. We're, in this case, thinking of contexts in which labels, in which humans can label, like it's a task that is achievable by human coders. In general, that reflects sort of a philosophical commitment of mine about the quantities that we care about in social science. So I think mostly, if we're getting things, mostly I think when we ask questions in social science, it is my contention, and I'm happy to talk about this more in Q&A, that that sensible quantities that we want to infer are ones that we could write down kind of coding rules for. Now, those might be subjective, but I think effectively making that commitment to saying I can write down coding rules is sort of a way of kind of making your approach to measurement, your approach to estimation, vulnerable to being wrong. Because if you commit to a gold standard, right, it's much easier to say something like, I mean, it's difficult to talk about accuracy with respect to some, latent quantity of interest that we want to learn, absent the capacity to write down coding rules and define a gold standard. There are exceptions to that, and again, I'm happy to talk about that more generally, but it's certainly true that labels can be subjective. Even if we can define coding rules, human coders obviously are prone to error, so that's true. But there's a lot of work obviously thinking about how to validate and assess the quality of human coding. Anger, Scott asks, is anger one of the modes of speech that can be identified? Yes, so basically what we're assuming is that you have some labeled data. If you can label data as angry or not, then it's a thing that could be estimated. Now, it would presume that it could be labeled. So I pause momentarily for those questions after zooming in. I will zoom back out and zoom back in. Oh, that's not what I meant to do. So we zoomed in. And so what I'm showing you now, again, are particular projections of the data. So each black dot is one frame. So one slice of time in an utterance. And then on the x-axis, on the left x-axis, so there are two plots here. In the left plot, the x-axis is the energy, so basically the loudness. And on both, the y-axis is basically the sort of resonance frequency. You can think about it as it is formally the first formant. And so, and then the right axis, or the right plot of the two, the x-axis is a zero crossing rate. And so what am I showing you? So each of these different, again, as I mentioned, black frames or black dots are frames. So these extremely short little chunks of time, in this case, from that speech by Obama that I showed you. And so the same black dots, the same, or each black dot appears in both of these frames. The distribution of them is slightly different, again, because the features are different. So we're taking different slices of the data. And the model that we developed, the lower level component of that hidden Markov model, is learning to cluster these frames according to the sounds that we're inferring in this unsupervised way that then characterize each mode. So the green circles are denoting in both panels the same cluster that we've learned, but we're just cutting it differently because we've cut this high dimensional data. And so what you'll note is that this green cluster is, again, distinguishing some particular set of frames. And it turns out probably these are basically S sounds is what we've learned. We've learned sibilants, which is what that's called in linguistics. We can zoom out a little bit farther and look at more. And again, you'll note that in each of these, you can see that particular clusters that we've learned, these different colors, are denoting particular patterns in particular slices, right? So in some slices, we see similarities between clusters, and in others we see big differences. And that's, again, because those clusters may be similar in some dimensions and different in others. But we're basically learning to cluster these frames in this very high dimensional space of the data. Now, what's that good for? So I'm going to show you an example of kind of what we can learn. So in the following slide, I'm going, or in 2 slides, I think, I'm going to show you a particular, I'm going to play for you again that speech by President Obama. And I'm going to show you the clusters that we've learned in that speech. And I'm going to denote those clusters that are estimated by the model with the colors that I'm showing you on this slide. So the red is going to denote basically a kind of generic sort of absorbing cluster. So this is like a high variance, almost noise. Noise is the wrong word to use here, given the application to audio, but a sort of noisy cluster. Orange is going to be silence. Yellow is going to be loudness. Green is going to be this feature zero crossing rate, which is S's effectively and Z's. And then I'm going to let you try to infer what the model's learned about what blue is. And this is a totally unsupervised application of the model. So it's just learning clusters that are similar. And so the basic idea is we fit a model which is transitioning between those different latent modes according to some transition matrix. So let me play that for you. And again, as I mentioned, try to listen and infer what the blue portions of that speech are.
Voice can do. One voice can change a room.
To note
And
that
if it can change a room,
the yellows
change
have learned
the city.
vowels.
And if it can change a city, it can change a state. And if it can change a state, it can change a nation. And if it can change a nation, it can change the world.
So you probably now inferred rightly that the blue was sort of the audience sound, right? So it learned the sound of sort of audience cheering. Now, this is from, again, an unsupervised application. So the lower part of that model where we've learned the way a particular mode might sound just by clustering it. There was no label here though. And so in 2 slides, I'll show you a case where we're using labels and modeling each of those labels according to transitions like the one I just showed you for Obama's speech. A different way that I can represent the task that we're undertaking is with the following graph. And so what we're basically doing, not basically, what we're explicitly doing is imagining in some speech, which is occurring here in this graph from left to right, that a particular sound, a particular mode of speech is going to generate, or a particular utterance is going to be given by a particular mode of speech. So in this case, maybe sadness. There's going to be some metadata, which is going to govern what we're going to hear at that particular moment. We're going to transition in the subsequent utterance. Maybe in that case, we're happy. Again, that has some associated metadata. And that happiness, the sad mode of speech, the skeptical mode of speech, etc., the thing that we've learned given the labels brought by the researcher, is going to be associated with particular transitions between sounds. So this is where that unsupervised model that I just showed you is going to come in. And we might be transitioning between sounds associated with certain raw features. And that whole that process will continue throughout the duration of the speech. And so we can think about that in a particular application. So again, here too, so this is the broader context in which President Obama made that speech. So here is the text of speech. Here, if it can change a city, it can change a state. If it can change a state, it can change a nation. We can imagine that having labels like whether the president is in some sort of more pensive mode of speech or one trying to rouse the crowd, right, to kind of elicit a response. These transitions, again, occur between utterances. Within each utterance, we have words, which were spoken, again, over some audio wave, again, which had some particular set of sounds, each of which, again, is governing kind of what we heard. So the raw features that we observe, and this, again, our E panel here is mapping kind of to that. That's the level of the data that we looked at and the plot that I zoomed in on. So how does this work more practically? Again, as was asked, the researcher first has to think about sort of what are the tones of interest? What are the things we want to learn? What are the labels we're going to try to recover? The training set needs to then be labeled. We're assuming you're the experts here. You can determine that. We're agnostic as to the application. And then a model needs to be trained using, again, that training data. We use the trained models to naively label the full corpus, then use metadata to identify the patterns, and then refine those labels. So that's basically the way the whole algorithm proceeds. And then we have some proofs in the paper noting that this sort of stage by stage process jointly optimizes the model. And so with that, I will move to an application. So I mentioned that I was going to apply this to the Supreme Court. For this application, we collected a large corpus of audio. So we scraped from the OYE project about 400 hours of oral arguments for the 2010 to 2016 Natural Court. This has all sorts of metadata. It was 225 million rows with 27 covariates per row and about 185 gigabytes of audio. So this gets quite large, as you can imagine. The metadata included, again, stuff like, this is all from the SPACE Supreme Court database project. And so we paired each of these cases with associated metadata, which includes stuff like which side had which ideological orientation, the context of the case, so what are the related cases, the issues, and so on. And so we then, in this labeling task, coded 200 utterances for each justice, except for Justice Thomas. Followers of the court will quickly determine why, which is that Thomas never really speaks, so there's nothing to really label. In general, each of these utterances were about 10 seconds, about 20 to 25 words. And then the label that we pursued was basically whether or not the justice sounded skeptical. Now, that might sound like a subtle tone. One way that we've thought about this label and a way to describe it, and we decided on this label after listening to a ton of these oral arguments and determining that it seemed to be a continuously kind of present and learnable label. But imagine that you're giving a talk and think about the kind of questions you get from the audience. In my experience, there are at least two types of very distinctly sounding questions. There are the sort of questions which are very matter of fact, like, where did you get that data? Then there are the questions which are considerably more skeptical, right? And these are the questions like, like, where did you get that data, right? A question which seems sort of, to at its core question, the sort of general, say, pursuit that the researcher is engaged in. The way that Supreme Court justices are interacting with litigators is not very different, right? So sometimes a justice will ask a very matter-of-fact question. Other times we'll ask very, again, skeptical and almost pointed questions, much of which is not present in the text alone. And so I'll note that in a second. But another way to think about this is basically, if I were a lawyer, would I be happy to get a question that sounded kind of like this? And then we try to learn that label from just the tone of the utterances alone. I'll note this is a difficult test, right? We didn't start with an easy test, sort of, I think, subsequently to our great chagrin. There's a lot of crosstalk, so people talking over each other. There's background noise. These are relatively subtle labels, pretty diverse. And it's highly imbalanced for some justices. So some justices very rarely are skeptical or are very rarely not skeptical. And so Justice Ginsburg was one such justice who was a particularly difficult task in our prediction exercise here. We did a lot to validate the model. I've moved much of this to the appendix, but I'm happy to talk more about it if you have questions. But the model predictions, I'll note, are on their face skeptical and neutral. So we seem to have some good face validity. And in general, the audio contains a lot of information that isn't in the text. So the out of sample performance is much better than text classifiers, to the point where most of the text classifiers attempting to recover these labels strictly from the text did no better than random guessing. There were very, very, very few words or words themselves that correlated with that tone. So when we tried to figure out why the text models were doing so badly, if you look at just raw correlation of terms to these labels, there is basically none, with few exceptions. And importantly, the tone is predicting voting better than affective words. So when we tried to look at this as a prediction task with respect to votes, which a lot of people in political science attempt to do, the tone predicted voting better than the words of speech that the justice used. In the auditory profile, so the features themselves within the labeled categories differ substantially, which again is consistent with these being both meaningfully different labels and labels which are learnable in audio. And so first, I'm going to validate the model briefly by just identifying Supreme Court justices. So here we're going to imagine that the category of interest, the label of interest, isn't something like anger, it isn't skepticism, it's who is speaking, right? So again, our model is relatively agnostic with respect to what the label is. So we can just as easily try to learn the speaker identity as we can learn the speaker's affect in some way. And this is a pretty straightforward task, right? So this is a this is a task where gold standard labels are considerably easier to imagine and consider, right? So here you can think about this as being a task where there's no disagreement about the truth. So you can think about this again. So here we have 11 coarse modes of speech. That is speech by which justice. So mode 1 is speech by Alito, 2 by Breyer, and so on. You can imagine this, while we use this to validate, this isn't totally beyond the bounds of what we'd ever do as researchers. So we have an ongoing or early stage project in which we're having undergraduates deliberate amongst each other on a series of issues, where we've also embedded treatments in that deliberation. And so the data comes to us as a series of recordings. And so we're using the model basically to determine who's speaking and when those speakers transitioned. And we've done, some work on that workflow, which I'm happy to talk about as well. So what do we do to do this? So we're going to draw 100 utterances per justice. We're going to then, so 1,100 utterances in total. And then we're going to evaluate out of sample prediction or predictive accuracy by k-fold cross-validation. We use 100 instead of more utterances because that's on the scale of utterances that we labeled, right, for the skepticism application. And we evaluate, again, out of sample accuracy with k-fold cross-validation, which is sort of standard. And we did so, again, training a model specifically for each of those folds, so that, again, as one ought to, all of our tests were on truly held out data. And then we're going to benchmark this with a widely used Python library for audio classification. It's one of the only alternative packages for like feature extraction and analysis in R and Python. And we benchmarked it against a range of models. So we're going to use our hidden Markov model against a bunch of things like SVMs, random forests, etc. None of which, importantly, directly are modeling speech dynamics. And by that, I mean, these are not models which look at the data as being temporally ordered and organized in the way that we can model data with a hidden Markov model. And so we're going to look first at the best model in out of sample accuracy. So on the left, we have the true speaker for each utterance. On the bottom, we have the predicted speaker. So this is just a confusion matrix, if you've seen confusion matrix before. So for Ruth Bader Ginsburg, 96% of the time, the best model learned was correct with respect to, on a given utterance, identifying the speaker, in this case, Ruth Bader Ginsburg. About 1% of the time, it confused Ginsburg with Kagan. About 1% of the time, it confused Ginsburg with O'Connor, and so on. We can do this for all justices, and we see that Ginsburg was a uniquely easy case with respect to classifying speaker identity. So in a perfect world, on that diagonal, each of those cells on the diagonal would have a value of 1. John Roberts is particularly difficult. So Roberts ends up getting confused with Kennedy a lot, confused with Breyer, and so on. And we're only right 62% of the time on what's a relatively easy task, I think. So the overall accuracy across all speakers was 85%. With the model that we trained, our accuracy was much higher. So we ended up having, or in this case, in our out of sample predictions were correct 91% of the time with Roberts compared to 62% with that SVM from the Pi audio analysis library. And that put our overall accuracy around 97%. So here I'm plotting now, again, a series of different models. So this is just each of the blue dots are competing approaches. The red dots are predictions from our model, and then across a range of hyperparameters. So we can vary hyperparameters in each of the different alternative models and also within the HMM. And you'll note that mostly it isn't even the case that we picked a particularly outlying model, that across even different values of tuning parameters, there seemed to be a marked performance from moving to a hidden Markov model. So I'm going to wrap up quickly now by applying this to oral arguments. So oral arguments are sort of one of our only windows into the kind of behavior of justices on the court. And so we might ask, how and why do they deliberate? There's a huge, again, kind of literature on this. Some people think that oral arguments have no purpose. This is some old papers by Siegel and Spaeth, others. And the idea here is that justices have really stable voting preferences. The case information is really well established by lower courts, briefs, etc.
I think.
Oh, and some justices, it turns out, have said things to this effect. So predictably, Justice Thomas, oops.
I think it's unnecessary to decide in cases to ask that many questions. And I don't think it's helpful.
Now, again, as I mentioned, Justice Thomas never really talks in oral arguments. And so that's not altogether surprising. Alternatively, we might think that justices collect additional information about cases and so on through the argument. And so there's also literature suggesting this. The idea being that briefs don't contain wholly reliable information. Justice might need additional arguments to achieve policy goals. And then a third idea would be that they're trying to persuade and inform each other, right? So where 2 is, they're trying to basically inform themselves. 3 is they're engaged in political signaling, trying to convince other people on the court. And so there are some arguments about this as well. And so I'm going to throw Sotomayor into this camp as well and play the following clip.
Sometimes we're talking to each other and we're raising points through the questions that want our colleagues to consider with us.
So what are justices doing in oral arguments? So it's difficult empirically to distinguish between these sort of informational and strategic models. There's an old paper now almost 30 years, I guess 30 years ago, that tried to demonstrate persuasion, or these persuasion effects. And so they attempted to do so by analyzing rhetorical style in hundreds of cases. They got through about 7 cases and then gave up. So there's some anecdote in that Schubert et al. Book. And so there's some observable implications, though, that we're going to link to, which is that we can ask sort of how justices question preferred versus opposing sides. So we contend that if justices are trying to persuade each other and to kind of strategically benefit the side that they want to win, we should see their kind of questioning favor the side that's ideologically inclined towards them, and also to be more strategically oriented in cases that are expected to be close. So votes that end up to be 5-4, right? And so I'll briefly show you some results and then conclude. So right now, I'm first going to show you the change in the predicted probability of expressed skepticism toward both favored and disfavored sides, comparing cases that are decided 5-4 versus 9-0. So in 5-4 decisions, justices are considerably more likely to express skeptical questions toward the side that they don't favor, the side that's not ideologically aligned with them, than they are in decisions that are ultimately unanimous. But they're also more likely to express skeptical opinions toward the side which is ideologically inclined, or to which they are ideologically inclined. So they are in general more skeptical in close decisions of the arguments put in front of them than they are in unanimous decisions, which is consistent with the notion that in tough calls, in decisions that they expect to be contentious, they seem to be particularly tough on arguments, even if that argument is ultimately on their ideologically aligned side of the aisle. And that's generally true across other ways of kind of, or other levels of other voting outcomes, right? So from, in both, again, unanimous and close decisions, they are in general showing some amount of, again, skepticism toward the side that they don't favor, but again, which doesn't seem to even change with the closeness of the ultimate vote. Now, it's complicated, and we don't view this as dispositive evidence one way or the other, but we mean to only illustrate the sorts of questions that one could potentially answer given an analysis of this sort. So this is an ongoing project. There's a tremendous amount of untapped data in audio corpora. I've linked in the chat a paper analyzing campaign speech. There are, of course, as this particular audience knows very well, tons of questions that can be answered and addressed with these sorts of tools for legislative speech, other tools on radio and television. We're working on extensions that jointly model the audio and the text rather than letting the text be incorporated as metadata, thinking about approaches that are, say, unsupervised or semi-supervised, and so on. So with that, I will conclude and see if there are any questions. Oh, there are more questions in chat, so I presume I should begin there. So the Yixiang linked the package in CRAN. There's an updated version on GitHub, which I should push to CRAN, in particular on a particular branch. So I have a graduate student working on improving the software. If you are interested in using the software, if you email me, I can point you to the latest version and also update you as that gets extended. Ichiang asked if this is better than using just vocal pitch. Yeah, so we didn't find, so there are two questions. One would be, I mean, I don't think we did an analysis using strictly the pitch. So in other work, so there are two ways you could think about using just pitch. You could use pitch and none of the other features, and then summarize each utterance as a vector of pitches estimated at particular moments, in which case you'd still be using a hidden Markov model, but you'd be using one with considerably fewer parameters. That would be worse if something like volume also mattered. My suspicion is, in general, other features almost always will have some additional information above pitch, like, for instance, zero crossing rate, which is, again, that kind of measure of sibilance. Another way of thinking about your question is, could we discard the temporal component and use just pitch summarizing the whole utterance? So take something like average pitch. There, I think you'd see, so in the linked paper, the second paper, the campaign speech paper, we found that what was especially important to the way that these pieces of speech are heard is not just the average of certain features, but also the kind of variance. And so at least in that particular application, reducing the data to something like the mean rather than higher moments like variance, or modeling that higher moment by this temporal order, is probably going to lose some information. A kitten, yes. Kitten noise might be confusing to Elise's question. Are there mature algorithms for established modes of speech? Yes. So there are some, especially for trying to detect, some of the earliest applications of these sorts of problems were to detecting, one particular application was to say automated like telephone stuff, right? So you call a hotline and you're asking questions. And so some of these algorithms were developed to basically try to decide, okay, this particular caller seems really angry. Should we pitch them to a human? Accordingly, there are some established libraries that wrap or that incorporate trained models on large amounts of data. So that exists. Yeah, there are. If you have particular questions, I can, if you shoot me an email, I'm happy to link to particular sorts of models. I think that's all the questions in the chat. I'll temporarily stop sharing my screen for a moment.
Have you, and I may have just missed this, but have you found that this is universal? Like, is this is it reliable and valid with all English speakers, all native English speakers? Do you find that it's influenced by culture, area, etc.? England versus US? You know, how, for lack of better words, how deep does the rabbit hole go?
That's a great question. So the way that we set the model up in this first paper, we are requiring that the human coder, that the model gets some information for every unique speaker, precisely because of this question, that we didn't want to take a position which was, we can learn about everyone from labeled data on some people, because obviously it's my contention that that's not the case in general, or at least not the case without a very representative set of labeled data, right? And in general, right, when we move outside the domain of the labeled data, I think we're unlikely to be able to learn a model that can do, at least in the general case, well without labeled data. So for instance, in your example, moving from say American English versus British English, you might in all sorts of contexts find that the model would perform worse. And as languages and cultures get more and more and more different, presumably that error would get higher and higher. Nonetheless, it is the case that we do want to be able to go a little bit outside the domain of the labeled data, more than requiring unique labeled data for every single speaker. So for instance, we have a project that has been on hold for a little bit where we were looking at speech in Westminster systems where we have hundreds of different unique speakers. We don't want to label hundreds of or data for hundreds of different people separately. And perhaps in those systems, we think, okay, they're all from the same country. We could do empirical checks to see how well we travel out of sample. So we're working on cases so the model learns kind of optimally from different speakers. But any case like that, where we're trying to label outside of where we're trying to make predictions outside of where we have labeled data, I in general think one ought to bring a great deal of caution to those sorts of applications.
Thank you very much.
Scott, I have a question.
Yeah, thanks, Chris. I appreciate your presentation. I'm sorry I'm such a novice here, but I study incivility and legislative discourse and so forth. And so I would like to, go to C-SPAN archives and try to listen for anger, spiteful, sort of sarcastic speech, often involved loudness. I know you said that's one of the things. And am I on the right path here? Is this something that could be done?
Definitely, yeah. I mean, I think there are a lot of ways to think about. One of the reasons I like requiring labeled data is I think that, like, one way in general that I think about machine learning is, like, if a human can hear that thing, like a model can, it is possible to learn it in a model. Maybe it requires a lot of data, but if you can hear it, right, you're just your own little model too, right? Like, we're all doing computations. There's some model in your head that is learning this. And so, if you were wanting to find stuff like very contentious pieces of speech in say C-SPAN archives, I think if it's a thing that could be like heard from an RA, I think it's a thing that could be learned from a model. What is optimal with respect to discovering those things probably depends a little bit on the use case, but definitely, I think that's extremely tractable.
Thank you.
Yiqiang.
So thanks for the presentation, and I probably have a question regarding to the recording conditions for like observational study, right? Like for Supreme Court or the campaign speech, like many of them are not like recorded by a single device, so that could be like for many different conditions when people are doing the recording. I thought that might interface with like corresponding whatever the labeling or the classification tasks that will be conducted in the future.
Yeah, definitely. That's a good question. So we do a lot of, like, here we do stuff like standardize the features. So I didn't talk about it now, but we do things like standardize the features. Loudness is a really good example of this, right? As you probably can infer, if a microphone's really far from one justice and close to the others, and then they switch seats, right, if they were to be in different places in a different recording, then we'd have incomparable recordings across those justices. All these things can be problems. So there's some component of that can be dealt with by pre-processing, like by standardizing, by removing background noise. There are good algorithms increasingly, right, for doing stuff like removing background noise. We try to identify things that are like crosstalk. So if you leave in crosstalk, that can be tricky. So I think step one is a pre-processing step to try to address these things as well as possible in the features themselves. I think a benefit, again, of something like labeled data is that if the labeled data is representative over those different recording contexts, then we could observe that the heterogeneity and error over those contexts in, say, a validation test. Like, we could hold out whole speeches and see that we do worse on some speeches than on others because of some, say, variation in recording features. So in the context where we have labeled data, that's a thing that could be empirically tested. So we'd at least be able to observe it, but it's a really good point. Robert?
Yeah, do you think there's any relationship between when you did the Obama speech, we were watching the visuals.
Mm.
Did the visuals enter into this at all, or not?
That's great. Another good question. So this is part of what motivated it. So in the paper that I didn't present, the one that I linked, we did an experiment where we took campaign speeches from Obama and Romney, and we found over the course of the campaign trail, we found cases where they said a particular piece of speech that was almost the same. So they'll have these little talking points, like some statement about energy, say. And so they'll say the same thing in Providence in a small, quiet presentation that they say in a stadium out in LA or something like this. We found cases where they said these same things, but they varied in the way they delivered them. And we gave the speeches, so then we created, for each of these, we found 29 pairs like this. And then we created, we did the following experiment. So subjects saw this pair of speech, and they saw either just the text, which was basically the same. They saw the audio, or heard the audio, or they heard the audio and saw the video. So we basically zeroed out other channels. So we zeroed out the sound, or we zeroed out the sound and the video, and so on. And what we found was that when they looked at similar text, obviously they mostly just guessed. There were small differences in some of the text. So, but in general, it looked like they were just guessing because there's no difference. We asked them to code these on a bunch of different things. There's no difference between the text, but the audio and video, there was a lot of difference in how these pieces of speech were perceived, even though the text was the same. We didn't see many differences though, from the moving from the audio to the video condition. Now, I think a lot of that's not because the visual component doesn't matter. I think a lot of it is like a lot of the work on, so some of the earliest stuff on maybe visual stuff was like the spatial competence coding, right? And there people were showing some correlation between like whether or not someone looks like a competent leader and vote outcomes. So maybe part of the reason we didn't find stuff is because it was Obama and Romney, and every single, we're comparing Obama to Obama, right? So we're not varying the face itself or the competence of the speaker, right? So in general, again, Obama's going to be giving the speech pretty well. So that's a particular test. I think there are other cases where the visual features probably will matter a lot. Like my bet is that it doesn't matter altogether that much. If you ask me to bet, it doesn't matter altogether that much in legislative speech because no one's doing that much with visual components in a legislature, right? It's Ted Cruz being Ted Cruz, one or the other, even if he pulls up a little poster. But that it matters tremendously for something like news reporting, right? Like, the whole, or maybe again, like that old example with, what was was it Kennedy? It was that you could hear the debate versus watch it, and the exit or the interviews after the debate suggested that people who listened to the debate had very different impressions than people who saw and listened to it.
Kennedy Nixon.
So what was that?
Kennedy Nixon debate.
Yeah, Kennedy Nixon, right? That was the one. So I don't think there's any hard and fast rule, but yes. So the shorter answer is yes, I bet it matters. But it's probably more of a question of when does it matter and for what kind of measures.
Good, very good. Any final questions here before we let Chris go? It's been, there's a lot of stuff in the chat. There's some new postings of an article. And we'll put up Chris's email in a moment here so that you can send him questions. And again, we really want to encourage people to think about this kind of research and sort of as a graduate seminar in a way. What are your ideas? So think about that and send Chris or I your ideas, and we'll see if we can help make them happen. So, Andrea?
I want to thank Dr. Lucas for sharing his expertise today in the video research and audio research. And I want to thank everyone here for joining us today. If you missed any of these workshops, we will be posting videos on our website this summer. You can also check us on Instagram and Twitter. And just a reminder that call for papers is open for the 2022 research conference this fall. Accepted from submissions will get their papers published in the Year in C-SPAN Archives Research Book, Volume 9, and will receive a $2,000 stipend. I'm going to ask Dr. Browning just to give you a little bit more on this before we let you go.
Yeah, well, every fall we have a research conference. We don't know exactly the shape of it yet for the fall, both in terms of the papers and obviously because people are only putting their proposals in now, but also whether it will be hybrid or in person. Things are opening up, but you never know exactly what the university's position will be on in-person conferences. They haven't released that yet as we move out of the intense COVID period. But basically, any paper, as it says in the far right circle, they extract text or data from the C-SPAN video library, analyzing. We've had papers by historians who use the archive to document their narratives. We've had people who've analyzed video. We've had a lot of people who analyze text using different software like sentiment analysis, for example. And so it's wide variety at this location there called Docs Live Purdue EDU CCSE. All the books are available through 7 volumes. The 8th is in print, is in production now. And so you can see what people have done and download any of the pieces and write your proposal and submit it at the site.
Okay. Again, thank you everybody for being here today. Please feel free to reach out to myself or Dr. Browning anytime if you have any questions. And we are absolutely happy to keep this series going this fall. So thank you all very much, and we will see you this fall.